All right, please turn in what you have. Go. Thank you. Thank you. Anybody else? Last call. There you go. Thank you. All right, let's get down to business. There's a stack of quizzes going around from last week, I think. Where's that stack of paper? It's getting around? Okay. All right, so I'm not going to go through this. I'm just going to talk about it. So obviously you have to do power rule. I mean, this is all basically just, do you remember power rule for antiderivatives? So you just do this term by term. That one is what, though, when you do antiderivative? Natural log, right? And then your answer needs a plus C at the end. All right, this one is a little harder, right? What do you have to do first? Yeah, there's a couple of things. One thing you could do is do this over this, this over this, this over this, and then rewrite them as all powers of x, and then do your antiderivative. Or I heard someone say you can bring the root x up. That's another thing you can do. Either way, you can't just do the antiderivative of each one separately. Cannot do that, all right? Because we have division here. We can only do antiderivatives piece by piece if we have addition and subtraction, all right? So there's a problem in the homework like this. I don't think it had a square root in the bottom, but it had, I think, 3 terms over a single term. All right, so hopefully we'll see how the quiz went, and then we'll talk about it next time. Are there any questions? Before? Did you what? Oh, did you forget plus C on this one? So look, in the beginning of this class, I'm going to be a little bit lenient with the plus C, okay? But by the time we get, you know, the further along we go, the more strict I'm going to be about the plus C. I mean, there are some professors who will count it completely wrong if you forget plus C, because you're only giving one answer, right? And I'm asking for the general antiderivative, which is an infinite number of answers. There's a family of functions. So the plus C creates the family. So you're missing an infinite number of answers without the plus C. So I can understand how some professors would take off everything, but I'm just going to kind of give you a little slap on the wrist in the beginning, right? But just remember plus C every time you do antiderivative. Okay, so looking at our schedule, today we're going to do 5.5, the substitution rule, and then next Monday we have a holiday. It's Labor Day holiday, so we don't have class. Then we come back and we're going to do integration by parts. We're going to start doing integration by parts. We might even start it today. And then we have an exam. So next week we don't have class Monday, we have class Wednesday. Then the following week we come back Monday, your first exam. That first exam will cover everything up through what we get through next week. All right, so whatever we finish with on Wednesday of next week is fair game for the exam. In my opinion, this first exam is the easiest exam of the semester, by far the easiest exam of the semester. And it's an opportunity for you to really get yourself off to a good start, all right? So you want to be prepared for that, you want to be ready, and yeah, any questions? We ready to get going? Y'all okay? All right, so we're going to do 5.5 today, and this is called the substitution rule. So what we did last time is we learned that basically we know how to find the antiderivatives of things from Cal 1 that we remember we can go backwards from, and we also know how to do antiderivatives of x to any power, as long as that's by itself, right? And that's it. So now we move into the first technique of finding antiderivatives. I also said last class, this first couple of weeks is going to be all about us learning how to find antiderivatives. We'll see what we're going to do with them later, but let's just get good at doing it. So in terms of the different ways to find antiderivatives, we're going to learn a couple of different things in this class. The first major thing we're going to learn is called the substitution rule. That doesn't look right. Substitution rule. The next thing we're going to learn is integration by parts. Next thing is trig integrals. Then we're going to learn this thing called trig substitution. I'm just going to put trig sub. And then we're going to learn partial fractions. All right. Those are, when it comes to finding antiderivatives of things, these are the main ideas in Cal 2. These are the main techniques we learn. All right? Today, we're going to talk about the substitution rule. Okay? And I would say, in my opinion, that difficulty-wise, these progressively get harder to do. All right? They get more challenging to do. That's just my opinion. And the reason they get harder is because to do an integration by parts technique, you have to be good at the substitution technique. To do trig integrals, you've got to be good at these two. To do trig sub, you've got to be good at all of these. And then to do partial fractions, you got to, you know what I mean? It's like you're not going to be able to go up to the next level unless you feel real good about the previous level. So you can't have any holes here in this stuff, all right? So trig sub, substitution is our first technique. All right, so here's how it goes. I want us to look at two different problems, okay? I want us to find the general antiderivative I'm going to give you two different functions to look at. The first one, f of x, is x squared plus 1 over x. And I'd like for you to contrast that with this function. I'm going to call this one g of x, just so that it's not the same thing. And I'm going to put x over x squared plus 1. Right? Very, very subtle difference between the two, right? All I've done is flipped it over, right? So let's talk about the first one. Can you find the antiderivative of this? How would you proceed to do that? Split it up, right? You could split this up. So to do this problem, you could split this up into x squared over x plus 1 over x, right? Make two terms out of it. You're allowed to do that because you have a single term on the bottom, right? And then this is just, what, x plus 1 over x? So this, or x to the negative 1. So this original function can be rewritten, right? Now you can find the antiderivative, right? Now you can find the antiderivative. So I think we could do this one, right? Given that we all did our homework and feel good about what we did. The antiderivative of this would be antiderivative of that. X squared over 2, or 1/2 x squared. I'm going to always put the this as a fraction out front. I'm always going to do that. You could write this as x squared over 2, though. It's perfectly fine. And then plus, now the antiderivative of 1 over x, natural log of absolute value of x. Right, don't forget the absolute value on the natural log.
Are you taking points
on the quiz, on this one, again, it's just going to be a little, but going forward, it has to have absolute value on it. Okay, plus c. All right. Okay, so this problem works out. We don't need anything special other than a little bit of algebra and then power rule and then what we know about 1 over x, right? Any questions there? What about here?
That would make you x.
We're not, yeah, we're acting like we don't know that yet, right? So for this, can you split it up? You can't split it up. And because you can't split it up, we can't use the same method. And so we get stuck here, right? We kind of, at this point, don't know what to do, all right? So we're going to have to introduce this new thing called the substitution rule, or U substitution, as I'll put the notes up in a second, all right? But we need something new to be able to handle something like this, all right? Before we do it, we're gonna start to get some new notation in place. It's going to make our lives a little bit easier. Now, I don't know, easier. It's just going to help us communicate the math better. I'm getting sick and tired of writing find the general antiderivative each time, right? So how about some new notation? New notation. All right. And it's just notation, right? Notation is always just symbols and things like that to help us communicate with each other, right? If I put a plus symbol, everyone understands what I'm doing, right? So it's just notation, how we write something. So instead of me writing down, hey, find the general antiderivative of something, here's what I'm going to write instead. I'm going to write this symbol. It's an S that's been stretched out vertically, okay? And then what I'm going to do is put next to it the function I'm talking about, f of x. And then next to this f of x, I'm going to write dx. All right, that's the new notation. So I want to explain what everything is here. These things have names. This right here, this big thing right here, is called the integral sign. Now I'm going to show you, remember how I've told you this now 3 times, that we're going to learn how to do antiderivatives first, and then we're going to see what we can do with it, right? We're just learning how to do it, and then we're going to go build something with it, right? I've told you this. So for right now, I want you to just say, hey, that's a symbol. I don't care where it comes from, why we chose to use it. I'm just going to ignore that. Later on, I will show you that this symbol actually does make sense, all right? It's going to it represents something that has to do with taking the sum of something, all right? But right now, we're just going to look at it as a stretched out S, call it the integral sign. This right here, the function that you're actually looking at right here, this is called the integrand. It's kind of like in college algebra when you had like a square root. The thing underneath the square root was called the radicand. I don't know if you remember that, but that's what it was called, the radicand. Well, here, the function that you're actually trying to find the antiderivative of is called the integrand, all right? This piece right here, which causes a lot of people headaches, this piece right here is called the differential. And that piece right there, all it does is keeps track of the variable that you're finding the antiderivative with respect to. Okay, pay attention to what I'm saying. Do you remember in Cal 1, when you differentiate, you always need to know what you're differentiating with respect to. Like, are you differentiating with respect to x or with respect to t? What's the variable that's independent versus dependent? And so this is keeping track of the independent variable for the antiderivative, right? So that's what that is, all right? Now, this answer, right, whatever the answer is to this, when you find the this is telling you, go find the antiderivative of that function. Your answer, I shouldn't have put this here. This equals some capital F of x, right? That's the actual antiderivative, isn't it? Then plus some constant. So this right here is the actual antiderivative. And then this right here is called the constant of integration. The constant of integration. Now, all of this is in your notes, all right? I just really wanted to put it on the board because I wanted you to see it. Where we go? Hold on. There we go. So this is all in your notes, all right? Given a function f of x, we wish to find general antiderivative, then we write that notation right there, okay? The whole thing, this whole thing together, all right? All of this right here, all of that is called the what? Everything right here in red is called the indefinite integral, okay? This is called the indefinite integral. Later on, we're going to learn about something called the definite integral. This is the indefinite one. The indefinite one, it's called indefinite because think about your answers. Your answer is a family of functions, right? It's not one particular function, it's an entire family. So you're not quite sure, you're not definite about it. It's an indefinite integral, right? And then I already said this is the integral sign, this is the integrand, that's the differential, and then that's the antiderivative constant of integration. The process of finding antiderivatives, the actual process of doing it, is called integration. In Cal 1, the process of finding derivatives or taking derivatives is called differentiation. In Cal 2, we're finding antiderivatives. It is called integration. Got it? All right. So let's see how we're going to do this substitution. So this is just notation. I'm going to get it off the board here in a moment. I want to go back to this problem right here, but I'm going to start over. Quick show of hands. Those of you who took Cal 1, how many of you saw U substitution in Cal 1? A couple of you, U substitution? All right. So from the show of hands, about half of you have seen this, maybe. So let's do this problem right here. The one that I just put up there. All right. Isn't that the same problem as I had here a second ago where I put g of x and I put that there and I said, hey, go find the antiderivative? That means exactly the same thing. Go find the antiderivative, right? But the thing is, we don't know what the antiderivative of this is. We can't do anything like splitting up, so we're stuck, right? So then we start thinking about what do we know? What have we learned about antiderivatives? Well, so far nothing, right? Except the power rule and stuff. So, but now there's this thing called substitution. So what is it? What is substitution? So here's the actual steps. If you want to look at it as steps, there's not much to it, and it's somewhat hard to explain. So here are the steps that I teach my students. All right, this is called I don't have it. The substitution rule. So we're trying to basically undo a chain rule, but let's just do the problem. All right, so here are the steps. First thing I'm going to do is I'm going to look at the integrand, right? So you're looking at this, you're focusing your attention on it, you're thinking about what you're seeing, right? And what I'm going to do, step 2, is I'm going to try and look for something in the integrand, okay? Something that I'm actually going to call something, all right? I don't know what it is yet, but it's something. I need to find something in here, all right? I need to see it, identify it. And then when I see this something, I need to also see its derivative there as well. All right, so you're trying to find something. You're looking for something in that integrand and its derivative. So when you look at this, does anyone see something and its derivative, okay, and its derivative, where the derivative that you see has to be in the numerator, and it's okay if the derivative is off by a constant? So I know it's confusing first time you ever see this. Go ahead.
X squared plus 1.
X squared plus 1. Let's just, for those of you who are like, what the hell is he talking about? Just let's go with this. If I say that the something is x squared plus 1, everyone see the x squared plus 1 is on the bottom here? Okay. What is the derivative of that? 2x. Everyone agree? So the derivative of that, the derivative of the something, right? The derivative of that something is 2x. Do you see that over here anywhere? Well, you see an x, don't you? You don't see 2x, but you see x, right? Is the x that you see in the numerator? So is that derivative that you're seeing in the numerator? Yes, right? Is it trapped in a parentheses or underneath the square root or anything like that? No. Is this thing here and the derivative, are they off by a constant? Yes. So going back to the steps, look at the integrand, look for something, right? Here's my something. And then try and look for its derivative. Okay, the derivative of this is 2x. Ah, there's a 2x, but I'm off by 2. It's okay to be off by 2. But that thing is up in the numerator and it's not trapped. That's what it says I'm looking for. Something and its derivative. The derivative should appear in the numerator and not be trapped. and the derivative might be off by a constant, which in this case it is. Kind of getting this? If that's the case, if you can find something and its derivative and it, all those conditions are met, then here's what you do. We are going to make a substitution. We're going to let u be equal to the something. Okay, this was just me thinking through it, all right? This is actually me doing the substitution. What I'm going to do is something we've done in math almost our whole lives, and that is make a substitution. Replace something with something else. So I'm going to replace I'm going to replace x squared plus 1. I'm going to replace it with u, all right? So where I see an x squared plus 1, it's going to be replaced with u. But if I do that now, I'm going to have a u down here, I'm going to have x's up here, right? What I need is to get, if I'm going to make a substitution to switch to u, the entire problem has to be switched to u's. Not just, you can't have u's and x's mixed together. All right, not till Cal 3. That's when you can start mixing things like that, and it's something else. But here we have to get everything in terms of u, or everything, keep it in terms of x. So I now need to figure out how I'm going to handle this x and this dx that are still here. So what we do is we take this u, and we're going to do something, we're going to do some Cal 1 to it. We're going to take the derivative on both sides of the equation with respect to x. Do you all agree that if I'm calling u this, then the derivative of that with respect to x would be 2x? Yeah? Well, the dx is over here, right? I have du over dx is 2x, right?
In terms of u, so we move the dx.
Exactly, yeah. So I have 2x here, right? I have 2x. I'm off by a constant, but see, this has a dx here, doesn't it? And so what I'm going to do here is I'm going to multiply both sides by dx. And so I get du equals 2x dx. Quick recap. I'm going to replace this bottom piece, right? I'm going to replace this bottom piece here. That's going to be replaced with u, right? That's going to be replaced with u. And what I'm trying to do is replace the x dx with something that has u's in it. And do you see I almost have it here? But see, the 2 is a problem, right? So what I'm going to do here is just multiply both sides by 1/2. Right? If I multiply by 1/2, I get x dx there. And now, these are exactly the same. Let me rewrite the original integral. I'm going to rewrite it this way, because I think it might be easier for those of you who might be a little bit lost on this. It might be easier if I rewrite it this way. Because this x is in the numerator, and this is times dx, I can slide the x to the side like this, right? It's the same problem. And now, if you look at it this way, do y'all see everything? I can replace everything now. I can replace this piece here, right? It's going to be replaced with u. That's going to be replaced with u. And then the x dx, right? That's this, is going to be replaced with 1/2 du. Questions? Let's do it. Let's write it out, and then maybe when I write it, you'll see everything there. And so I'm going to have antiderivative 1 over what? U, right? That's 1 over u, times, this is just 1/2 du. Yeah, so when it comes to antiderivatives, right, when it comes to antiderivatives, 1 over u, right, is what we're trying to find the antiderivative of. The du, again, is just keeping track of the variable. Now our variable's u, not x, right? The 1/2 is a constant. Since 1/2 is a constant, when we take the antiderivative, constants come for the ride. We did that all last class, right? If the constant was there, we just brought it with us. So a lot of times what we'll do is we'll bring the 1/2 in front of the integral sign and then put 1 over u du. So it's like you're pulling the constant out and saying, hey, this is just going to come with me. I'm really just trying to find the antiderivative 1 over u. You can always pull constants out in front of the integral. You can never pull variables out. Y'all hear me? You can never pull a variable out of an integral.
Is that like the limit rule?
It's like the differentiation rules. Yeah, it's the differentiation rules that constants just kind of tack on to the front. It's the same thing in reverse. All right, now, yes?
Why would you pull a constant out? What was your reasoning for that?
Because it just gets in my way. It just bothers me to see it, so I just put it out here so I don't have to think about it for a little while. And then all I'm doing is I'm thinking to myself, what's the antiderivative of 1 over u? Natural log of u though, right? Of u, absolute value of u. And then the 1/2 will be tacked on to the front. So this will be 1/2 times, now at this point I'm actually going to give you the antiderivative, right? So since I'm giving you the antiderivative, I no longer have an integral sign because I'm actually giving you the antiderivative. It is natural log of the absolute value of u. Now, we need a plus c, for sure, right? We need a plus c. Students will always ask me, though, what happened to this? They always go, what happened to this, right? Like, I understand that the antiderivative of this is this. And students are like, what happens to the du? The du is just keeping track of the variable. That's all it is. That's all it's there for, is to keep track of what variable is. So when you go and you actually take the antiderivative, you can ignore it, all right? You can actually ignore it. I've told my Cal 1 students, if they need to like have this become something over here, then make it become the plus c, even though that's technically not right. I mean, like this right here, this becomes, well, the 1/2 comes, and then this antiderivative is natural log of the absolute value of u, and then the du, where does it go? Oh, it becomes the plus c, so you don't forget about it, all right? Yes?
So, but without saying plus c, because you said that's not technically correct.
Yeah.
What happens to the d? It's just down.
It's not going, it's just keeping track of the variable. So look, let me give you an example. Let me try and illustrate it this way. Okay. If I write down f of x equals 2x, and I ask you for the antiderivative right now, okay? So I say, hey, what's the antiderivative of this? General antiderivative. You would say capital F of x equals x squared plus c, right? That's what you would say?
Yeah.
Okay. Now, our new notation would look like this. What's the antiderivative of 2x, right? But that, if I ask for the antiderivative, this would be our notation, right? But I would need next to it to have correct notation dx. That just keeps track, that's just reassuring you that the variable, the independent variable in this problem is x. So this, from here to here, right? From here to here, that is the same as what this is asking you to do. So your answer is still just x squared plus c. The antiderivative of x squared, 2x is x squared. The dx, again, was just the notation to keep track of the variable. So it's not going anywhere. Does that make sense? Or
Yeah.
it's just part of the notation. All right. Yes?
You say it's kind of like how f of x is designed to say this function with respect to x. It's kind of the same.
Exactly, yeah. This is a function, right? This is a function with respect to x. See, again, this goes back to, or this goes to where calculus goes at some point, all right? So later on, Cal 3, which I know not all of you have to take, you'll have functions of more than one variable. So you'll have functions where you have, I mean, all the functions we deal with in this class are one input, one output, right? X goes in, you get something out, right? But later on, you can deal with functions that have multiple inputs. 3 inputs and maybe 1 output, or you could have 3 inputs and 2 outputs, or 3 inputs and 5 outputs. Yes?
So the dx is just saying that that's the constant of the x function.
That's the independent variable. That's the thing being plugged in. It's assuring you that that's what's being plugged in. So like here, whatever this is, if I define a function, if I want the antiderivative, right? Let's say I define this function. I saw someone's hand. Hold on. Let's say I define this function x squared plus y times z. All right, I'm going to just define a function like that. And now I want to know the antiderivative of that function, x squared plus yz. I need to tell you right now what I'm treating as the variable and what I'm not treating as a variable. And so I need to put here d something so you know. Otherwise, you don't know which I'm treating as the variable. It turns out you cannot treat them all as variables simultaneously. You have to do them one at a time. So I would do something like this, and that would tell you, oh, you're going to take the antiderivative of this with respect to x first. So you're going to treat x like the variable. You're going to treat these like constants. And then maybe after you're done with that, then you'll do another antiderivative and treat y as the variable. So you'll have another integral and then a dy here. And that's called a double integral. And then you take care of the z and you have your third integral dz, and that's called your triple integral. Okay, so I'm just trying to get you to see again, this is like a placeholder for the independent variable. Okay, I saw a hand.
So it's just, so you don't forget you made a substitution, so you can put the substitution.
Yeah, and it works, it helps us also with the substitution, right? But the thing I think that people get lost with, I guess, is like they know this becomes something over here, and they want this to become something over there too, but it doesn't become something. And if you can't get your head around that, then fine, make it become the plus c, even though that's not right. Yeah? Okay. All right, let's do another problem.
So,
Yes.
do you not have to go back to x?
Oh, sorry. I got distracted. I apologize. Thank you for reminding. I do have to go back to x here. Natural log, absolute value. What was u?
X squared plus y.
X squared plus 1. So you do have to replace it back to x squared plus 1. Thank you for bringing that up, because technically our answer is not complete because we left our answer in terms of u. We needed to replace that u back to the x squared plus 1. Good news. You could always check your answer, right? Like if you took the derivative of this, you should get back what was in the integrand to begin with. That's if there's any like good news in Cal 2, you can always check your answers. All right, how about this one? All right, is there anything that, don't go straight to substitution, can we do this? We know the antiderivative cosine of sine, right? So is the answer to this just sine of 5x? No, why is the answer to this not just sine of 5x? Chain rule, right? Let's say that you thought that the answer to that was sine of 5x plus c, right? Let's just say you thought that was the answer. Well, check your answer, take the derivative. If you take derivative of this, what's derivative of sine of something? Cosine of 5x, right? Times, now you have to take derivative of what's inside, which is 5, and then plus derivative of constant is 0. So this is 5 times cosine 5x. That's not what that is over there, right? This doesn't have that 5, does it? So that didn't work. So maybe substitution. Look at this. Do you see something and its derivative as well, and it's okay if the derivative is off by a constant? This one's a little tricky. It's almost so obvious it's tricky.
5x.
The 5x? What do y'all think? If I let u be the 5x, what's the derivative of that?